Hi everyone, today I'm going to give you a revision class for DGE-106 Calculus 2, and we will talk about the first order linear differential equations and also the second order linear differential equations. So if you turn on the revision slides that I give you in the Google Classrooms, you will see that I have some slides for you for chapter number 4, chapter number 5, and chapter number 6. So let's talk on the chapter number 4 first. So as you can see here in the green box, we have the first order linear differential equations, and that is given to you in the standard form in the first expressions, which is dy by dx plus pxy equivalent to qx. And then after you rearrange the given expressions into the standard forms of the first order linear differential equations, you can follow the 3 steps to find out the functions of dy. And the first step is that you have to first be able to find the px and the qx term first, and second step, after you know the px functions and then the qx function, you can find an integrating factor based on the px term by taking the exponential or an integrating factor of the px dx. And then the last step, you will multiply both sides of the equations by the value of the integrating factor, which I will show you in the example. Alright, so let's go to the example number 1 first. Suppose that you are given with the y prime plus 3x squared y is equivalent to 6x squared, and then you are asked to solve the first order linear differential equations of these given equations. Alright, so if you could remember from the slides I just showed you, we have to first rearrange the given equations into the standard form first, and that's equivalent to the qx. So this is the standard form that you have to rearrange the given functions into the terms inside the yellow box here. So right, you can see that this is the first order differential equations, because you can see the y prime notation, the top notation here, and then that y prime basically is equal to the y divided by the x plus 3x squared y is equivalent to 6x squared. So if you compare the expression number 1 with the standard equations inside the block here, you can see that this is our px. Therefore, the first step here to identify the px, where our px in this case is equivalent to 3x squared. Alright, and then the second step, you have to find an integrating factor. So an integrating factor, remember that is equivalent to the exponentials or the px terms dx. Alright, and in this case, our px is 3x squared. So you have to find an integrations on the 3x squared functions with respect to the x, right? So in this case, when you have to find an integrations of the x squared dx, so remember that it is equivalent to x power of 3 divided by 3. So if you cancel this 3 and this 3 here, so you will end up with the x raised to the power of 3. Therefore, the integrating factor is equivalent to the exponentials of the x cubed. Alright, and then we are done with the second step, and the third step is to multiply I equivalent to the exponentials or the x cubed on both sides of the expressions, and that should be expressions 1 here, right? This one. So if you multiply that the exponentials of x raised to the power of 3 on both sides of the equations, you will have this term, right? Okay, And then I would like you to focus on the left hand side of the explanations here. If you take a look at this result carefully, you can see that it comes from the product rule between the value of v multiplied with the value of y. But our v in this case is the integrating factor. So let's describe the product rule first. So remember, the product rule is the combinations between the v, okay, the v functions multiplied with the differentiations on the y, adding up with the function y multiplied with the differentiations on the v term. So that is how the product rule is described. And if you compare that with the product rule between the integrating factor, which is the exponentials of the x cubed multiplied with the y, so you will end up with the terms inside this box. So let's try to prove that together. So in this case, it is the product rule or the combinations between the integrating factor terms and the y terms. So we have the exponentials of the x cubed multiplied with dy by dx plus the y terms multiplied with dy d by dx, and also you perform the differentiations on the exponentials of the x cubed terms. So the first term here, it becomes the integrating factor multiplied with dy by dx, which is the same as what we have inside the box, and then we have to find the differentiations on that exponential term. So the differentiations on the exponential functions is equivalent to the exponential functions itself, and you have to multiply that with the result of the differentiations on the functions of that exponential, which is the x cubed. So you will have the you have 3 multiplied with the exponentials of the x cubed multiplied with the x squared. Alright, and if you try to rearrange that expression here with the combination with the y's, you will have 3x squared y's, and then you will have the x raised to the power, or the exponential of the x raised to the power of 3, which is the same as what we have inside the block. Therefore, on the left hand side of the equations, you can summarize that it is equivalent to the product rule between the integrating factor terms and the y terms with differentiation sign. Okay. Therefore, on the left hand side of the equations, you will have d divided by dx, and then you have the integration sign here, and that's equivalent to and that's equivalent to the 6 multiplied with x squared, the exponentials, or the x cubed. So we are done with that step, and then the next step we have to perform an integrations on both sides of the expressions. So that should be y here with respect to the dx. So we have to do that on both sides of the expressions as well. So we will have that with respect to the dx. So these integrations, which means the antiderivative and derivative. So antiderivative and derivative can be cancelled out. Therefore, this one you will have left with the integrating factor terms multiplied with the y on the left hand side of the equations, and on the right hand side of the equation here. So you have to find an integrations on that 6x squared multiplied with the exponentials or the x cubed. So there are basically there are 3 main ways to find the integrations. The first one is by substitutions, the second one is by parts, and the third one is by using the partial fractions. So in this case, we will try to use the substitution first, and if it does work, then we will follow that step, right? So in this case, if we let u to be equivalent to x cubed, therefore du would be 3x squared dx, right? So we have 3 terms. We have the x squared, we have the x, which can be abstract out from this integration function here, right? Therefore we will have 2, and then inside the integration sign we have 3x squared e raised to the power of x cubed dx, right? So in this case we have 2 and then 3x squared dx here, that is basically equivalent to the du, all right? And then we have left with the exponential terms, and we let u equivalent to the x cubed at the beginning, therefore e will be raised to the power of u. So you will have 2, and then you will only need to perform an integration on the exponential of the du terms. So integration of the exponential is equivalent to the exponential functions itself additional with the constant c. So in this case we have to convert the variable of u back into its original variable, which is in terms of the x. Therefore we will have to substitute u as the x cubed plus c. Therefore on the left hand side of on the right hand side of the equation here, we will have 2 multiplied with the exponentials of x cubed and then plus c. Therefore our ultimate goal is to find the functions of the y. So we will move these functions onto the right hand side of the expressions. So we will have 2 multiplied with the exponentials of the x cubed multiplied with that negative terms plus with that negative terms multiplied with the c. So that one and that ones can be cancelled out. Therefore our y is equivalent to 2 plus with c multiplied with the exponentials of negative x cubed. Sorry, that should be x cubed, right? So this is our final solution for the first order linear differential equations without any initial conditions, all right? And then the example number 2. So in the example number 2 is still stick with the first order linear differential equations. For example, if you are given with the x squared y prime plus xy equivalent to 1, and then some initial conditions is given to you here, which is y of 1 equivalent to 2. So first step, you have to transform the given equations into the standard form first. So in this case you have the x squared dy divided by the x plus y multiplied with the x equivalent to 1. So if you compare that with the standard form for the first order differential linear equations, which is dy by dx plus pxy is equivalent to the qx, some functions of the qx, you can see that we have to delete or we have to eliminate the terms x squared here. So since we have to eliminate the terms x squared here, in this case we will have to divide that x squared on every terms and also on both sides of the expressions, and finally we will end up with dy divided by dx plus this x and this x. So we have 1 divided by x and multiply with dy is equivalent to 1 divided by x squared. So this is our standard form of the equations x squared y prime plus y x equivalent to 1. And then the first step, after we rearrange the given functions into the standard form first, we have to subtract out for the px term. So in this case, if you compare that, we know immediately that our px is equivalent to 1 divided by x, all right? And then next we have to find an integrating factor. So our integrating factor here is equivalent to the exponentials of an integrations of px dx terms. So in this case our px is 1 divided by x, all right? So integrations of 1 divided by x dx is equivalent to the ln of x. Therefore we will have the exponential of ln x. So based on the property of the exponentials and the initial logs and the natural logs, we found that the value of integrating factor is equivalent to x. Alright, and the third step, we have to multiply both sides of the expressions, okay, by the value of I equivalent to x on these standard expressions. Therefore, we will have dy divided by dx plus 1 divided by xy is equivalent to 1 divided by x squared. And we need to multiply that by x, we need to multiply that by x, we need to multiply that by x term as well. So again, on the left hand side of the expressions, it's similar to when you perform the product rule between the x terms and the y term. Alright, so that would be equivalent to x multiplied with dy by dx plus y multiplied with the x by dx, which is basically equivalent to y, right? So that is the same as these ones. So therefore, in this case, on the left hand side of the equations, we can summarize that the functions inside this block here is basically equivalent to the differentiation between the product rule of the x and the y's, right? And then the right hand side of the equation here, after you eliminate 1x, you will have left with 1 divided by x. Alright, and then you need to perform an integrations on both sides of the equations with respect to the with respect to the x terms, So again, this one antiderivative and this one is the derivative, antiderivative and the derivative can be cancelled out. Therefore, you will end up with x and y term left. And that side here, so you will have to perform an integrations of 1 divided by x, which is basically equivalent to ln of x plus c. So therefore, our functions of y here in this case is ln x plus c divided by x when you move x on the left hand side toward the right hand side of the expressions. But remember that in these questions, you are given with some initial conditions, which is y1 equivalent to 2. Alright, so you have to find the value of c based on the initial conditions y of 1 is equivalent to 2. So you will substitute the value of x equivalent to 1 back into these expressions, and the whole of that functions will be equivalent to 2. So ln of 1 is 0 plus c equivalent to 2. Therefore, our value of c is equivalent to 2. Alright. So after you know the value of constant c, you have to substitute it back to the value of to the function of y. Therefore, our final function of y in this case is equivalent to ln of x plus 2 divided by x. So that is our final solutions for these first order linear differential equations with the initial conditions. Okay, and next. Oh, sorry for that. Okay, so next is the chapter number 5. Here is about the second order linear differential equations. So if you could remember in the chapter number 5 here, so you can see that in the chapter number 5 here, in this case, okay, let me go back to that. Okay, so in the chapter number 5, we have two different types of the functions for the second order differential equations. The first one is the homogeneous functions, and the second one is the non-homogeneous functions. So here, in this case, when you have the second order linear equations and your right hand side of the equations is equivalent to some gx functions, we describe that kinds of equations as the non-homogeneous equations. However, if your gx is go into 0, like in the second explanation here, you can describe that kinds of equations as the homogeneous equations, right? Okay, and then after you identify whether it is the homogeneous or the non-homogeneous equations, you will have to find the root for the equations, and there are three possibility cases that could be occur in the second order. The first one's when you have two different real roots or two distinct roots. So if you know that your roots are different, then you have to express your yc or the complementary solutions as y equal to c1 multiplied with the exponentials of the r1 x plus c2 multiplied with the exponential of the r2x. However, if you have two repeated roots, then your complementary solutions will have to be written in these theorems, like in theorem number 4. So you have y equal to c1 e raised to the power of r1x plus c2x. You have the additional of x multiplied with the exponential of r2x. But again, these r1s and these r2 remain the same, so they have the same value. However, if you have found that you have two complex roots, then the complementary solutions will have to be written in this way as stated in the theorem number 5. So that will be equivalent to the exponential of the alpha x multiplied with c1 cosine beta x plus c2 sine beta x. So you have to be able to identify the value for the alpha and the value for the beta. Alright, so that is for the second order homogeneous differential equations. Okay, so we will go back to the example, and then you will have the clear picture of the second order ones, right? So let's see the example 3 together. So if you are given with y double prime plus 5y prime plus 6y equal to 0, and then you are given with two different initial conditions. The first one is for the y 0 equal to 2, and the second one is for the y prime of 0 equal to 3, right? So if you take a look in this case carefully, you will see that you have to find the second order differential equations. So if you could remember that if we try to substitute the value of y as the exponential of the rx terms, alright, and then your y primes, your functions of the y prime would be the r multiplied with the exponentials of the rx. So in other words, you perform the differentiations on the y functions, you will end up with that r multiplied with the exponential of the rx. And also y double primes is you perform the differentiations on the y primes, which is the differentiations on r multiplied with the exponential of the rx. And again, this is the product rule between one term and another term. Alright, so that will be equivalent to rd divided by dx multiplied with the exponential term adding up with the exponential terms multiplied with the differentiations on the r. But remember that this r here is the root, which means that it is the constant. So differentiations or the constants will go into 0. Therefore, your second term will go into 0. However, your first term here will be the r multiplied with the exponential of that x terms, and you will have to find the differentiations on the function of the exponential, which is the rx terms. So therefore you will have, so that one will be the r. Therefore y double prime is equivalent to r squared multiplied with the exponential of the rx. Okay. And then next step, after you know the value of y primes and y double primes, you will have to substitute that functions and that functions back into the given expression here, right? So in that expressions, you have y double prime plus 5y prime plus 6y equal to 0. So we know that y double prime is equivalent to this term, so we can substitute that. and then also y prime as well is equivalent to r multiplied with the exponentials of the rx, and also likewise the value of the y or the function of the y is equivalent to the exponential of the rx, and that's equivalent to 0. So as you can see, we can attract the same common term, which is the exponential of the rx. Okay, and then inside the parentheses you will have the r squared plus 5r plus 6 equivalent to 0. So if you try to move these exponential terms on the right hand side of the equations, it will go into 0. Therefore, you will have left with r squared plus 5r plus 6 equivalent to 0, right? And then up to this step, you will have to find out the functions for the value for the roots. So in this case, it can be expressed as the r plus 2 multiplied with the r plus 3 equivalent to 0. Therefore, your r1 is equivalent to minus 2 and your r2 is equivalent to minus 3. So that falls into the case number 1. When you have two different roots, so you have to use these functions of y to form the complementary solutions, right? Therefore, our yc here is equivalent to c1 multiplied with the exponentials of the r1, which is minus 2x, plus c2 multiplied with the exponential of the r2, which is equivalent to minus 3x. So that is the yc, alright. And if you go back to the equation here, you can see that you are given with two different initial conditions, then which means that you have to find two different values for two different constants. But the conditions that are given to you in terms of the y functions and the y prime functions. Therefore, after we know the functions of yc here, we have to find the yc primes in order to substitute the initial condition back into the statement conditions. So in this case, we have to find the differentiations on that yc equations. So that would be minus 2 multiplied with c1 is raised to the power of minus 2x, minus 3 multiplied with c2, and also multiplied with the exponentials of minus 3x. So that is the conditions for the yc. So let me name that as equation 1 and let me name that as equation 2. So after that, we know from the statement that y0 is equivalent to 2. Therefore, we can just summarize that the expression 1 is equivalent to the value of 2. And also same as equation number 2 here, when you have the y prime 0 equivalent to 3, therefore we can just summarize that expression 2 here is equivalent to the value of 3. So let me name that as the expression 3 and the expression 4. So in this expression 3 and the expression 4, we have to substitute x as 0 here, this one x as 0 and this one as the 0. Therefore, you will have c1 plus c2 equivalent to 2, and you will have minus c1 minus 3c2 equivalent to 3. So that is, let me name that as A and let me name that as B, right? So in the expression A and the expression B, so suppose that if I let c2 equivalent to 2 minus c1, right? And then from the expressions A, we know that we know that minus 2 c1 minus with 3 multiplied with c2, but c2 in this case we have to substitute with 2 minus c1 is equivalent to 3. So that would be 2 minus c1 minus with 3 multiplied with 2 is 6, plus with 3 c1 equivalent to 3. So therefore minus 2 and plus 3 becomes c1 is equivalent to 3 plus 6. Therefore our c1 is equivalent to 9. Oh, sorry, our c1. Right, this one should be c1. Sorry for the mistakes. And then we know that C1 is equivalent to 9. Therefore, based on these conditions, we can be able to determine the C2. So C2 is equivalent to 2 minus C1, where C1 is 9. Therefore, our C2 is equivalent to minus 7. So after we substitute two initial conditions back into the statements of yc and yc prime, then we can be able to determine the value of C1 and the value of C2. Therefore, when you have to answer for the yc, the solution to that second order differential equations, so therefore we know that the yc, or the solution to that second order, is equivalent to 9 multiplied with the exponential of minus 2x minus with c2, which is minus 7, multiplied with the exponential of minus 3x. So that is the solutions for the second order homogeneous equations when you are given with two different initial conditions, and then two value of the constants will be determined, right? And next, okay, so in next slide here, for the homogeneous linear equations, when you have the functions for the gx, then you have to make a guess for your particular solutions, or the yp here. So your yp can be able to determine based on your function gx. Suppose your gx here is given in terms of the exponential. Therefore, when you make a guess for your particular solutions yp, you can make a guess like the a multiplied with the exponential of that beta t. And likewise for the trigonometric sines and cosine, when you have sine terms and when you have cosine terms, then when you make a guess, you have to make a guess for both sines and both cosine terms. And again, your beta t here, is based on your given functions in your gx term. For example, if your gx is equivalent to cosine of 5x, therefore when you make a guess for your yp should be cosine your yp should be cosine of 5x plus sine of 5x, right? And also you need to have the constants a and b in combination with sine and then cosine, right? And also if you are given with the polynomial functions for your gx term, you have to estimate for your yp particular solutions based on the highest degree of your polynomial. For example, if your gx is equivalent to 5x squared here, so you know that the highest degree is 2. Therefore, your estimations for the yp should be ax squared plus bx plus c until the end of your degree, right? So that is the concept of the homogeneous linear equations. So let's go into the example here, right? So this is the example number 4. So suppose you are given with y double prime plus 4y prime plus 4y equivalent to 4x squared plus 6e raised to the power of x. So you have to understand that this is the non-homogeneous equation first, and then if that is the case, you have to find two different functions in order to solve for the solutions of your second order. Remember that your solutions of the second order homogeneous equations, or y, is equivalent to the combinations between the yc adding up with the yp. So your yc can be determined by letting gx equivalent to 0, and your yp here can be determined by estimations of your gx functions, and then you will make a guess for your yp. Okay, so first things, let's try to find the yc first. right? So your yc here, like I said at the beginning, that when you let the gx terms equivalent to 0, therefore you will have the y double prime plus 4y primes plus 4y is equivalent to 0 first. So that is your complementary solutions. And again, in this case, you have y double primes and you have y primes. You have y. You have to substitute the functions for y primes and y double primes based on these functions here that we determine, right, based on these functions. Okay. Therefore, in this case, after we substitute that, we will see that we will end up with the r squared multiplied with the exponential of the rx plus 4 multiplied with the r multiplied with the exponentials of the rx plus 4, right? And then that's multiplied with the exponential of the rx equivalent to 0. So the rx term, the exponential term here can be deleted out. Therefore, you will end up with the r squared plus 4r plus 4 equivalent to 0. So next step, you have to find the functions for the r that's similar to what we did in the example number 3. So in this case, we have two repeated roots which is minus 2. Therefore, we can summarize that our R1 is equivalent to R2 and that is equivalent to minus 2. So if that is the case, therefore your YC is equivalent to C1 multiplied with the exponential of minus 2x plus C2x multiplied with the exponential of minus 2x. So that's it, your YC, right? So we are done with this YC. And next we have to find the YP by using an estimations for your GX terms. So YP here can be estimated from the function of gx. So the gx in this case is given as 4x squared plus 6 multiplied with the exponentials of the x. So we have both terms. We have the polynomials and also we have the exponential functions. So therefore your yp is equivalent to the combinations of the polynomial functions and the exponential function. So let's start with the polynomial function first. So in this case, the highest degree of your polynomial is 2. Therefore, you will need to have 3 different constants. So that is ax squared plus bx plus c. And then for the exponential functions, so you have to make another estimations for that exponential function which is equivalent to a multiplied with the exponential of the x. But again, you have already used a, therefore in this case for the exponential you cannot use the constants or the variable a. So let me make that as d. Alright, so after you find the functions for the yp by making a guess from the gx terms, therefore you can be able to find y primes and y double primes for your yp. Therefore yp primes is equivalent to 2ax plus b plus d multiplied with the exponential. So basically you have to perform the differentiations on these functions for the yp, and then your y double prime here would be 2a plus d multiplied with the exponential of the x, right? Okay, so next steps. So you have to go back to the equations, right? So the equations give you that you have y double prime plus 4y prime plus 4y equivalent to that gx term. So in this case, you have to substitute the yp double primes, yp prime back into these functions. Okay, therefore, let me repeat the equations for you first. Plus 4y equivalent to 4x squared plus 6 e to the power of the x. So in this case, we will substitute y double primes as yp double prime, so which is 2a plus d multiplied with the exponential terms of the x plus 4 multiplied with that y prime, where that y prime is this one. So you have 2ax plus b plus d raised to the power of the x plus 4y, where y is basically equivalent to the yp. So you have ax squared plus bx plus c plus d multiplied with the exponential of the x equivalent to that the x terms also remain the same. Okay, and then next step, after you substitute things yp double primes, yp primes, and yp back into the functions statement here, and then next step you have to find the similar coefficients. So let me start with the x squared first. So you have to find the terms that consist of the x squared on both sides of the expressions. So let us take a look on the left hand side of the equations. Is there any terms that contain the x squared? Right, that is this one, right? So therefore we have 4ax squared equivalent to that 4x squared on the right hand side of the equations. And next, so is there any terms that contains the exponentials of the x on both sides of the expressions? So again, in this case we have that we have this one multiplied with the 4, we have this one multiplied with 4 as well. So therefore we have de raised to the power of x plus 4 de raised to the power of x plus 4 de raised to the power of x equivalent to 6 multiplied with the exponential of the x. Alright. And then next we have to find the x terms. So you have to find the terms that consist of the variable of x on both sides of the equations, right? So if we take a look at that carefully, we can see that we have these ones. We have 4 multiplied with the bx terms, okay? So we have ax plus 4bx equivalent to 0. Why equivalent to 0? Because there is no terms that consist of the x variable on the right hand side of the expressions. Therefore we can summarize that it is equivalent to 0 on that side. And then the remaining term would be for the constant. So we have this 2a, we have this plus 4b, we have this plus 4c equivalent to 0. Since there is no constants on the right hand side of the equations, therefore we will make that as equal as 0, right? This x squared and this x squared can be cancelled out. Therefore we have 4a equivalent to 4 left. So our a is equivalent to 1 in this case. And again, likewise in this case as well, we have the exponential of the x can be eliminated out. Therefore that size we will have 9d equivalent to 6. Therefore our d is equivalent to 6 divided by 9. In other words, it is 2 divided by 3. Right, that's for the value of d and a. And next we have xa plus 4b equivalent to 0. So in this case we will find the value of the b, since we know the value of the a, which is 1. So the value of b in this case is equivalent to minus 2, right? Since you move 4 on the right hand side of the equations, therefore it will become minus 2. And then the last ones, you know that a is 1, we know that b is minus 2, and then the only value that we don't know at the moment is c. Therefore we have to find the value of c, right? So 2 minus 8, that becomes minus 6, and then plus with 4c equivalent to 0. Therefore your 4c is equivalent to 6, or in other words, c is equivalent to 6 by 4, or is it 3 by 2, right? So now you know for value for the four different constants, which is a, b, c, and d. And then next step, you will have to substitute this value of a, b, c, and d back into the functions of yp. Okay. So therefore, remember that our solution to the second order homogeneous solutions is y is equivalent to the combinations between the yp plus with the yc, the complementary solutions. Again, the complementary solutions is found when we let gx equivalent to 0, and the yp is found by making an estimation for the gx terms. So remember that our yp here in this case is equivalent to ax squared plus bx plus c plus the exponential of x. So we have to rewrite that again. And then adding up with the yc complementary. So yc, we have already found at the beginning that it is equivalent to c1 multiplied with the exponential of minus 2x plus c2x multiplied with the exponential of minus 2x. Right. Then you have to substitute the value of a, b, c, and d back into the yp functions, and that after that you will know the solutions for the second order linear differential equations. So we know that a is 1, so that would be equivalent to x squared plus b. So our b in this case is minus 2x, and then plus c, that is 3 divided by 2, and then plus d, where d is 2 by 3. So you have 2 by 3 multiplied with the exponential of the x plus c1 multiplied with the exponential of minus 2x plus c2x multiplied with the exponential of minus 2x. So therefore, this is our solutions to that second order non-homogeneous equations when the function of the gx is not equivalent to 0. Right, so this is the first order and the second order linear differential equation. Thank you for watching.